Hello, Professor. Welcome to this video. Here I'm going to be talking about the Minimax, Minimax, Alpha Beta pruning, and the WalkSat algorithm, the implementation of all those. So let's get started. Here we can see the class game, so which just basically implements the game class upon which the 2-ply and the 4-ply game has been implemented. So for and here we have the min-max algorithm from the book, that is 5.3. We can see that the max value, min value, and we are getting the value itself, the optimal value, along with the min, which calls the max value as a result. All right, and then we are taking the max of the game state of the different actions. So for instance, let's say I apply minimax or min-max algorithm on A. So the A is coming from the A player, the player A or the max, and when we do the min-max decision and when we call the game, which is the fig 5.2, right? Where is it? It's implemented. Yeah. So the fig 5.2 game. So here let's see the implementation of that. We have a dictionary that keeps track of the different connections to excuse me, the different connections to the preceding nodes or the depth of the node. So here A has different options such as A1, A2, A3. Now if we take the diagram as reference, A has different options, A1, A2, A3. And again, next is B, so that has different options such as B1, B2, B3, and C, C1, C2, C3, D, D1, D2, D3. So that's how it's implemented. Everything is a dictionary, and then we have the utility value or the utility function that the algorithm needs. Now here we can see that the utility is just the basic barebone values of the terminal nodes. Here it's the same thing. B1 has the value 3, B2 has value 12, B3 has value 8, and that has been just implemented here. So on for C and D as well. Now we are keeping a terminal state. Obviously we have different terminal states. Now we're just checking which node or which state belongs to max and which state belongs to min. Now for here instance, the state A belongs to max, right? But the state B, C, and D belongs to min. So it's the same thing. If the state is in B, C, and D, give me the min, else give me the max. So based on that, the utility value is going to get calculated. Now this is just the barebone figure 5.2. Now you've also asked to implement a 4-ply game, so to speak. 4-ply meaning four different players, or four different not four different players, four different the depth be to be 4 or 4 different turns, right? So we have let's say here now just instance, it's just a expansion of what we have built here. So I've built two more nodes, that is E and F, with different utility values. So for instance here, if we are in the nodes B, C, D, and F, then it is a min node. If anything else, it is the max node. So for instance here, A is the max node, B, C, and D min nodes, E max node, and F is the min node. So based on that, the utility value is going to get calculated, and again we can play the game. Alright, so let's say now we do the min-max decision on A on the game. So keep in mind, this game is coming from this variable that I've instantiated. Now game is fig2 game, that's the class, instantiation of the class. So that class has different methods, obviously. Now when we pass that game, the whole class, as to the algorithm with the initial node, now we have to get the optimal function, that is A1, or the optimal result, that is A1. So now we know that when we take the take the step, or the best optimal solution from A, node A is A1, that is goes to B, that is the max player. Now let's say for instance I take the value C. So now C is trying to optimize for the minimum, so we can have, the value should be C1. So let's say C, oops, so let's say C, yeah, and there you can see it's the value C1, right? So on and so forth. This can be extrapolated to any number of depth or any number of turns. Now let's, for example, get the extended game state, or the game which has different nodes. All right. So now let's say now I want to check out the E. Right now, for instance, E belongs to what? E belongs to max. E belongs to max, right? So we are trying to optimize the max. So the value ideally should be E3. So let's see. Um, all right, so we got back E3. So we are optimizing the max. Now let's say for F belongs to the min node, or the min part of the node. So we're optimizing for the minimization. Now F minimum should be F2. So go ahead and execute that. So we get F2 back. So we can clearly see that this algorithm is perfectly fine and working on different set of inputs. We just have to specify when we extend the nodes, we just have to specify, okay, what node does it belong to? Is it the min or the max? And then we also have to tell whether it's a terminal test or not. So that being said, this is the min-max implementation. Now the same thing we are going to apply on the alpha beta search or alpha beta pruning. All right, so for example, let me again go ahead and take the node E, and then when we execute that, we will get E3 obviously. And let's say I'll do B. We have to get B1, because for B we are trying to minimize, right? So B belongs to the min state. Now B min, so that is B1, that is 3. All right, so oops, that being said, where is it? A little down. Okay, yeah. So that being said, we have B1 for the alpha beta search algorithm as well. Now here the alpha beta search is pretty much doing this is the implementation of the 5.7 from the textbook. So it takes the max value and again the min value, and then checks the best action, the best score, by calling the min value, which in turn calls the max value. So yeah, so far so good. Now let's go ahead and check out the implementation of the WalkSat algorithm. Now this has been implemented obviously using the different clauses, random flipping values and variables. So we have taken the max flips of 10,000 with the probability 0.5, the satisfiability probability 0.5. So now obviously this the way we have implemented is by taking the converting the clauses to CNF. So now let's go ahead and see how this works. Obviously this has been reference from the AIMA GitHub repository. Now this is just getting into that repository because we want few dependencies, for example the utils, conversion to CNF, the logic, the expression, all that is needed for representing the values in terms of CNF. Alright, so the WalkSat algorithm. Now here we have taken different values, x1, x2, so on up to x6. So 6 different elements. Now we can see that, let me just zoom in a bit. So these are the 10 3 CNF randomly generated values of the clauses or symbols. So here we can see, for instance, x1 or x2 or x3 and not x1 or not x2, and not x1 or not x3 and not x2 or x3 and not x1 or not x3. So we can see now this has been implemented. Now obviously we instantiated this as different sentences or different literals using the expr method that we are getting from the AIMA GitHub repo, the utility function. So we have 6 different variables. So we can start representing all of them, all of these sentences. So sent1 is just the implementation or just the representation of the first, the first clause or the first sentence. So here we have x1 or x2 or x3, so on and so forth. So when we go ahead and apply that to the WalkSat algorithm, we get x3, x1, we get the model basically of different true or false values. So I've gone ahead and done this to all the different sentences, so from 1 to 10. And then I've also run the WalkSat from 1 to 10 using the time it magic function that is supported by the Jupyter Notebook. That gives us how much time it took to run a particular function, right, for every 100 loops. So now we can see that it takes about 16.2 millisecond plus or minus 167 microseconds per every loop. It is run on 100 times, so for every time it is, the average is coming out to be 60.2 milliseconds. So, and plus or minus 167 microseconds. I mean, that could be negligible, but we get the idea, right? So different sentences that has been implemented using WalkSat, and all of them, I mean, based on the probability of satisfiability, we can experience the Fig 7.919 of the diagram from the textbook. So yes, that is pretty much it. I think I've covered all the aspects. So the implementation, this is just a Jupyter notebook that I'm going to put around my GitHub, and also the video link on the GitHub. All right, Professor. Thank you. That's pretty much it. Thank you.